Here's a statement that's going to make a lot of hardware engineers uncomfortable. AI does not fundamentally fail at hardware engineering. You do. Not because you're not smart enough, not because you haven't read the documentation, but because the way most engineers are deploying AI for hardware design is, architecturally, completely wrong. And the scary part? The mistakes it produces don't look random. They look almost correct. A register assignment that's off by 1 bit, a bus with 2 drivers instead of 1, a clock domain that looks synthesizable right up until the moment you try to synthesize it. And here's what's really maddening about this. Engineers see those failures and they conclude AI just can't do hardware. They walk away from one of the most transformative productivity tools available to them. They dismiss the technology, when the real problem, the actual root cause, is the interface. It's the workflow. It's the fact that they're asking a large language model to do precision hardware engineering through a chat window. Think about that for a second. A chat window. The same interface you use to ask for recipe suggestions. That's how we've been trying to generate synthesizable register transfer level logic for billion transistor chips. Today on Mindcast, we're going to unpack why that approach breaks down at a fundamental mechanical level, and more importantly, what the research says actually works. This is not speculation. This is not hype. This is the engineering reality. And by the end of this episode, you are going to see AI-assisted hardware design in a completely different light. Welcome to Mindcast. I'm your host, Will, and this show exists for one reason: to take the most complex, most consequential ideas shaping our technological world and make them genuinely accessible and genuinely useful to curious minds like yours. Today's episode is built around a technical engineering research paper. I want to be upfront with you. This paper is not publicly available. It's the kind of deep, domain-specific research that lives inside engineering organizations and academic circles, rarely surfacing to the broader public. But the insights inside it are too important to stay buried. The topic is the intersection of large language models, the AI engines behind tools like ChatGPT and GitHub Copilot, and hardware description languages, specifically SystemVerilog. If those words don't mean much to you yet, don't worry. By the time we're done, they will. Here is the promise of this episode. You are going to understand, at a mechanistic level, why AI consistently produces flawed hardware code when used through conventional chat interfaces. You're going to understand the specific architectural reasons for that failure. And you're going to learn about a paradigm shift, a new engineering methodology called Spec-Driven Development, combined with what researchers call agentic feedback pipelines, that doesn't just improve AI output on hardware tasks, it transforms the AI from an unreliable copilot into something closer to a bounded, formal transpiler. Why does this matter right now? Because the pattern of failure we're going to explore isn't unique to hardware engineering. It is a case study in how to use AI correctly in any domain where precision is non-negotiable. Let's get into it. All right, key insight number 1. And this is foundational. Everything else we talk about today builds on this. The insight is this. There is a deep structural architectural mismatch between the way large language models were built and the nature of hardware description languages. Let me explain what I mean by that. When we talk about the training data that shapes an AI's understanding of the world, its intuitions, its patterns, its syntax preferences, we're talking about trillions and trillions of tokens. And the overwhelming majority of that training data is drawn from the software world. Python, JavaScript, Java, SQL. These languages represent a massive proportion of publicly available code on the internet, trillions of tokens. Now, how much of that training data is hardware description language, things like SystemVerilog, VHDL, or Verilog? Less than a fraction of a percent.
We're talking about a domain that is, from the AI's perspective, almost invisible. It is what researchers call a low-resource domain. The model has seen so little of it that its internal representations are shallow, poorly calibrated, and prone to confabulation, which is the technical term for what we colloquially call hallucination. But here's what makes it even more subtle than just a data imbalance. It's not just that the AI has seen less hardware code. It's that hardware description languages operate on a fundamentally different paradigm than software languages. Software like Python is sequential. Line 1 executes, then line 2, then line 3.
Hardware languages are concurrent. When you write SystemVerilog, you're not describing a sequence of steps. You're describing physical logic gates and flip-flops that all exist simultaneously in silicon, operating in parallel, synchronized to a clock signal every single cycle. That is a completely different mental model, and the AI, trained overwhelmingly on sequential software logic, imports that sequential intuition into a domain where it is categorically wrong. And there's one more technical layer to this from NVIDIA's own research on their Chip Nemo project. It has to do with tokenization. Standard AI tokenizers use an algorithm called byte pair encoding, or BPE. BPE is optimized for natural language and common programming syntax, but hardware languages have highly idiosyncratic syntax patterns, signal declarations, port maps, always blocks, generate constructs. BPE tokenizes these inefficiently, fragmenting the syntax in ways that obscure the structural meaning from the model. So you have three compounding problems: a massive training data deficit, a paradigm mismatch between sequential and concurrent logic, and a tokenizer that wasn't built for the domain. And the output of all three combined is exactly what engineers report seeing in practice: latches where there should be flip-flops, multi-driver buses that would short-circuit in silicon, bit-swizzle alignment errors that look plausible in text but are functionally wrong. This brings us to the second major insight.
Key insight number 2. And this one is where I want to really challenge some assumptions, because there's a very common response when engineers encounter the failures we just described. And that response is, let me just prompt it better. Add more detail to the prompt. Paste in the full specification document. Write a long, careful rules file. We've all tried it, and the research is unambiguous. For hardware engineering tasks of any real complexity, this approach does not work because of specific mechanical failure modes that happen inside the model's attention mechanism as the conversation grows. You start a chat session, you paste in the specification document for an HDMI interface. 200 pages, every protocol requirement, every timing constraint, every register definition. You feel good about this. Here's the first problem. That creates what researchers call attention dilution. The transformer architecture allocates attention, essentially focus, across the entire context window. When you flood that context with hundreds of pages of dense technical specification, the model cannot effectively isolate the 10 critical constraints that actually matter for the specific function you're generating. Critical information drowns in a sea of equally weighted text. Then the cascade begins. The AI generates some code with a small error, a bit slice off by one position. You don't catch it and move on. That incorrect code is now in the chat history, acting as a biasing signal that nudges the model toward repeating similar structural patterns. The error doesn't stay contained, it propagates. Register assignments downstream inherit the wrong offset. Interface contracts break. The whole design starts to drift from spec in ways that are increasingly difficult to trace back. And then there's what researchers call attention attenuation. As the conversation grows longer, the original system instructions you wrote at the very beginning begin to lose influence.
The model's attention is spread across thousands of tokens of subsequent conversation. That carefully crafted rules file you put at the top, by the time you're 50 exchanges in, it's essentially irrelevant. The model has shifted toward the patterns that dominate the recent context. Here's an analogy that captures this well. Imagine you put a sticky note on a CNC milling machine that says, "Cut precisely." That sticky note does not instruct the machine's control system. It does not enforce tolerances. It is a passive, human-readable note on a system that operates in a completely different language. That is what a rules file in a chat window is, relative to the precision requirements of hardware synthesis. And here's the crucial nuance. None of this is a fundamental limitation of AI. This is evidence that the chat interface is the wrong tool for this job. The capability is there. The architecture of how we're accessing it is broken, which is exactly what the research set out to fix. Key insight number 3. This is the paradigm shift. This is where the research moves from diagnosis to solution. And honestly, this is the part of the paper I found most intellectually exciting. The researchers proposed 2 interlocking innovations. The first is a methodology called Spec-Driven Development, or SDD. The second is what they call an agentic feedback pipeline. Together, they transform the AI from a conversational chatbot into something fundamentally different. Spec-driven development replaces ambiguous natural language instructions with formal, machine-readable micro-specifications. Instead of telling the AI, generate a module that handles HDMI audio, you give it a structured specification artifact, a precise interface contract defining every input and output signal, its bit width, its directionality, and its timing relationship to the clock. And you include SystemVerilog assertions, SVA, formal mathematical constraints that define what correct behavior looks like in terms the synthesis tools can actually verify. Here's why this matters. In an HDMI interface, you have 64 bits of audio data that must be precisely multiplexed across 2 audio channels over exactly 4 clock cycles. When you describe that in natural language, the AI has to translate your words into a mental model, then translate that model into hardware logic. Every translation is a potential source of error. When you encode it as a formal interface contract and SVA assertions, you remove the interpretation layer entirely. You're giving the AI a formal mathematical object and asking it to generate logic that satisfies it. That is a fundamentally more tractable problem. The agentic pipeline then wraps the AI inside an automated verification harness, calling the AI to generate a module, passing the output through Verilator for compilation, a linting pass, a simulation test bench, and feeding any diagnostic output back to the AI as structured, precise feedback. An automated system delivering exact compiler error messages and exact SVA violations in a closed loop automatically until the output passes all gates.
The research result is genuinely jaw-dropping. Passive chat rules achieve less than 30% defect recovery on complex hardware generation tasks. Agentic pipelines with SDD achieve over 90% auto repair rate on the same class of tasks. That is not a marginal improvement. That is a category change. What this implies is not that AI will replace hardware architects. The creative, systems-level thinking required to define what a chip should do, that remains deeply human work. What SDD and agentic pipelines replace is the manual, error-prone process of RTL entry itself. When you treat the AI as a bounded transpiler, when you stop asking it to improvise and start giving it formal objects to satisfy, the failure modes we discussed largely disappear.
All right, let's synthesize everything we've covered and land this with 3 concrete, actionable takeaways. Takeaway number 1, stop using chat windows for SystemVerilog generation. Full stop. If you've been using a chat interface to generate hardware modules, even with detailed prompts, even with extensive rules files, you now understand why that approach is mechanically flawed. The attention dilution, the context poisoning, the attenuation of system instructions. These are not bugs you can prompt your way out of. They are structural properties of the interface.
The replacement is micro-specification templates and formal interface libraries. Before you generate a single line of RTL, define the interface contract in a structured, machine-readable format. Every port, every bit width, every timing constraint, build a library of these. They become the ground truth that every AI generation is evaluated against. Takeaway number 2. Mandate SystemVerilog assertions for every AI-generated module. SVA is not optional in this workflow. It is the mechanism by which you make correctness criteria formal and verifiable. An AI-generated module without assertions is a module you're taking on faith. In hardware engineering, faith is not a verification strategy. Write the assertions first before you generate the implementation. Let the assertions be the specification. Require that every generated module passes them before it is accepted into the design. Takeaway number 3. Replace passive rules with active, closed-loop enforcement. Build or adopt an agentic pipeline. Wire the AI output into an automated verification harness. Verilator for compilation, your preferred linter for structural checks, a simulation test bench for behavioral verification. Make the feedback loop automatic. The AI should never be waiting for a human to read its output and type a correction. The pipeline should catch the error and deliver it back to the AI in a structured format, automatically within seconds. If you build that system, or adopt one of the emerging tools that implement it, you are not just improving your AI-assisted hardware workflow. You are aligning the AI's operating mode with the precision requirements of the domain. You are treating the AI as what it can actually be, a formal transpiler operating inside a constrained, verified environment. That is the shift, from chatting to constraining, from prompting to pipelining, from passive rules to active enforcement. Let's bring this home. We started today with a provocation. AI doesn't fundamentally fail at hardware engineering. Engineers fail because they're using it wrong. And I hope that by now that claim doesn't just feel provocative, it feels precise. We've traced exactly why the failure happens: the low-resource domain deficit, the sequential versus concurrent paradigm mismatch, the tokenizer inefficiency, the attention dilution, the cascade failures in long chat contexts, the attenuation of system instructions over time. And we've traced exactly where the solution lies: spec-driven development, formal interface contracts, SystemVerilog assertions, and agentic pipelines with closed-loop verification. A researched, benchmarked methodology with a documented 90+% auto-repair rate on complex hardware tasks. Here's the forward-looking thought I want to leave you with. We're at the very beginning of understanding how to correctly interface human expertise with AI capability. In every high-stakes domain, hardware, medicine, law, structural engineering, the early pattern is the same. People use the conversational interface, encounter failures, either dismiss the technology or search for a better workflow. The principles uncovered here, formalize your constraints, verify automatically, close the loop, are going to echo across every precision domain AI touches. The future of hardware engineering is not AI replacing engineers. It is engineers who understand how to constrain AI, replacing engineers who don't. Thank you for spending this time with me on Mindcast. If this episode shifted how you think about AI and engineering workflows, please share it. Subscribe wherever you get your podcasts, and check the show notes for SystemVerilog assertion resources, the Verilator compiler, and background on NVIDIA's Chick-Nemo research. I'm Will. This is Mindcast. Keep thinking deeply.